Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Combinatorial optimization, a field concerned with finding the best solution from a finite set of possibilities, offers a fascinating intersection of discrete mathematics, algorithm design, and real-world applications. Within this domain, the name of Éva Tardos resonates profoundly. Her work provides elegant solutions to computationally challenging problems, while also establishing cornerstones for entire subfields. Tardos' early career established her as a prominent figure through her innovative approaches to network flow problems, specifically her work on approximation algorithms. Network flow problems, at their core, deal with efficiently routing resources through a network. Think of pipelines carrying oil, data packets traversing the internet, or trucks delivering goods. The fundamental problem involves maximizing the amount of flow that can be sent from a source to a sink, subject to capacity constraints on the network's edges. Tardos, however, tackled a more intricate variant of the generalized flow problem. Generalized flow introduces a multiplicative gain or loss factor associated with each arc in the network. As flow traverses an arc, it's either amplified or diminished by this factor. Imagine a chemical processing plant where a reaction occurs as a substance moves through a pipe, either increasing or decreasing its volume. Or consider a financial network where currency exchanges along arcs result in gains or losses due to exchange rates. This seemingly small modification dramatically increases the problem's complexity. Finding the maximum generalized flow is known to be NP-hard, meaning that obtaining an exact solution in polynomial time is highly improbable, assuming P does not equal NP. Faced with this computational hurdle, Tardos ingeniously developed the fully polynomial time approximation scheme, or FTARS, for the generalized flow problem. An FTARS is a powerful algorithmic tool. It provides a solution that is guaranteed to be within a 1 epsilon factor of the optimal solution, where epsilon is an arbitrarily small error parameter. Crucially, the running time of an FTARS is polynomial in both the input size of the problem and the inverse of epsilon, 1 over epsilon. This ensures that as we demand higher accuracy, smaller epsilon, the algorithm's running time increases gracefully, remaining within polynomial bounds. Tardos' FTARS for generalized flow presented a significant breakthrough. Prior to her work, approximation algorithms for network flow problems often relied on linear programming techniques, specifically solving a linear program relaxation of the integer problem. While linear programming provides powerful tools, it can be computationally expensive, particularly for large networks. Tardos' approach, conversely, was entirely combinatorial. It operated directly on the network structure, iteratively improving the flow along augmenting paths until a near-optimal solution was reached. This combinatorial nature resulted in a more efficient and practical algorithm, especially for large-scale instances of the generalized flow problem. To elaborate on the mechanics of her approach, consider a network with nodes representing locations and arcs representing connections between them. Each arc possesses a capacity, limiting the flow it can handle, and a gain factor, dictating how the flow changes as it passes through. The algorithm begins with an initial feasible flow, typically zero flow on all arcs. It then searches for augmenting paths from the source to the sink that can accommodate additional flow. The key difference from standard network flow algorithms lies in how these augmenting paths are evaluated. Instead of simply considering the residual capacity of the arcs, the algorithm takes into account the gain factors. A path is considered profitable if the product of the gain factors along the path exceeds a certain threshold, effectively indicating that sending flow along this path will result in a significant increase in the overall flow reaching the sink. The algorithm iteratively identifies and augments flow along these profitable paths. After each augmentation, the gain factors and residual capacities are updated to reflect the changes in the network. The process continues until no more profitable paths can be found. At this point, the algorithm guarantees that the resulting flow is within a 1 epsilon factor of the maximum generalized flow. The polynomial running time is achieved by carefully controlling the number of iterations and by efficiently searching for profitable paths. A tangible example illustrates the algorithm's operation. Imagine a network designed to model currency exchange. Nodes represent different currencies and arcs represent exchange possibilities between them. The gain factor on an arc represents the exchange rate. For instance, an arc from US dollars to euros might have a gain factor of 0.9, meaning that $1 can be exchanged for 0.9 euros. The generalized flow problem seeks to maximize the amount of a target currency, say, euros, that can be obtained from a starting currency, say, US dollars, by strategically routing money through the network of exchanges. Tardos' algorithm would iteratively identify the most profitable sequences of exchanges, taking into account the exchange rates and transaction fees represented as capacity constraints, until a near-optimal exchange strategy is found. The novelty of Tardos' approach stemmed from its ability to circumvent the limitations of linear programming for this specific problem. While linear programming offers a general framework for solving optimization problems, it can be less efficient for problems with specific combinatorial structures. By exploiting the underlying structure of the generalized flow problem, Tardos developed a specialized algorithm that outperformed general-purpose linear programming solvers. This highlights a recurring theme in her work. A deep understanding of the problem's combinatorial properties allows for the design of more efficient and elegant algorithms. Her early work was undoubtedly influenced by the theoretical foundations of linear programming. The concepts of duality, complementary slackness, and the ellipsoid method, all central to linear programming, provided a backdrop for her exploration of network flow problems. However, she moved beyond simply applying linear programming techniques. She sought to develop algorithms that were tailored to the specific characteristics of network flows, leading to more efficient and insightful solutions. Tardos' FTARS for generalized flow had a lasting impact on the field. It demonstrated the power of combinatorial algorithms for tackling NP-hard optimization problems. It also spurred further research into approximation algorithms for other network flow variants and related problems. Specifically, her work influenced subsequent research on approximation schemes for multi-commodity flow problems and network design problems. Researchers built upon her techniques, adapting and extending them to address a wider range of optimization challenges. The influence of this work extends to individuals such as Serge Plotkin, who further further developed efficient algorithms for solving linear programming problems arising in network flow contexts, and David P. Williamson, whose work on approximation algorithms for a variety of combinatorial optimization problems was directly inspired by Tardos's approach to generalized flow. These researchers, among others, have cited and built upon Tardos's work, solidifying its place as a foundational contribution to the field of approximation algorithms. This early success, focusing on approximation algorithms for network flow, served as a springboard for Tardos's later, even more influential contributions to algorithmic game theory and mechanism design. Her deep understanding of optimization, algorithm design, and network structures provided her with a unique perspective on strategic interactions in networked environments. Her subsequent work built upon these foundations, addressing problems of network congestion, routing gains, and the design of incentive-compatible mechanisms. The pursuit of efficient algorithms for network flow problems, particularly the minimum cost network flow problem, occupied a central place in Tardos's research. This problem seeks the least expensive way to transport a specified amount of flow through a network, where each arc possesses both a capacity limiting the flow it can carry and a cost incurred for each unit of flow traversing it. Finding solutions that scale well, especially when the costs and capacities themselves are large, presented a significant computational challenge. Tardos made a breakthrough by devising strongly polynomial algorithms for the minimum cost network flow problem. The significance of this achievement lies in the algorithm's running time being bounded by a polynomial function of the number of nodes and arcs in the network, irrespective of the magnitude of the costs and capacities. This contrasts with weakly polynomial algorithms, whose running time depends on the size of these numerical parameters. Consider a network with 1 million nodes and arcs, where each arc has a cost and capacity represented by a 32-bit integer. A weakly polynomial algorithm might require time proportional to the value of these integers, potentially leading to impractically long computation times. A strongly polynomial algorithm, on the other hand, would solve the problem in time bounded by a polynomial of 1 million, offering a substantial advantage. Her approach involved a scaling algorithm, a technique where the problem is solved iteratively by progressively refining an approximate solution. Specifically, Tardos's algorithm employed scaling of both costs and capacities. The algorithm initially considers a relaxed version of the problem where costs and capacities are rounded to coarser values. Through iterative refinement, the algorithm gradually increases the precision of these values, converging towards the optimal solution of the original problem. To illustrate, imagine a small network with 4 nodes, A, B, C, and D, and 5 arcs A to B, A to C, B to C, B to D, and C to D. Suppose we want to send 5 units of flow from A to D at minimum cost. Each arc has a capacity and a cost per unit flow. The arc from A to B has a capacity of 6 and a cost of 2. The arc from A to C has a capacity of 3 and a cost of 3. The arc from B to C has a capacity of 2 and a cost of 1. The arc from B to D has a capacity of 4 and a cost of 5. Finally, the arc from C to D has a capacity of 5 and a cost of 4. Tardos's algorithm might begin by scaling down the costs, effectively ignoring the least significant bits. In the first iteration, arcs A to B, A to C, B to C, B to D, and C to D might have costs of 0, 0, 0, 0, and 0 respectively. The algorithm will then find a feasible flow of 5 units from A to D, perhaps sending 3 units along to B to D and 2 units along to C to D. In subsequent iterations, the algorithm refines these costs, gradually incorporating the finer details to adjust the flow and reduce the overall cost. The scaling of capacities works similarly, initially focusing on the larger capacity constraints before considering the finer limits. The complexity analysis of Tardos's minimum cost flow algorithm reveals its efficiency. The algorithm achieves a running time of order the number of nodes cubed times the number of arcs. This bound is independent of the actual costs and capacities in the network, a characteristic that distinguishes it from earlier weakly polynomial algorithms, such as the network simplex algorithm or the primal dual algorithm, whose running times can depend on the size of the cost and capacity values. The development of strongly polynomial algorithms for linear programming and combinatorial optimization holds profound implications. Linear programming, a fundamental optimization technique, finds widespread application in diverse fields, including resource allocation, scheduling, and logistics. Many combinatorial optimization problems, such as the traveling salesman problem and the maximum flow problem, can be formulated as linear programs. Therefore, efficient algorithms for linear programming have a broad impact on solving these problems. Prior to Tardos's work, the ellipsoid algorithm, developed by Leonid Kharchian, provided the first polynomial time algorithm for linear programming. However, the ellipsoid algorithm, while theoretically significant, proved impractical for many real-world problems. Kamar-Kar's algorithm, introduced shortly thereafter, offered another polynomial time algorithm with improved practical performance. Both the ellipsoid algorithm and Kamar-Kar's algorithm are weakly polynomial, meaning their running times depend on the size of the input coefficients. Tardos's work on minimum cost flow provided an important step towards strongly polynomial algorithms for broader classes of linear programming problems. Tardos's work built upon earlier research in scaling techniques for network optimization. Edmonds and Karp had previously used scaling techniques in their algorithm for the maximum flow problem. However, Tardos's algorithm introduced a new level of efficiency by simultaneously scaling both costs and capacities, leading to a strongly polynomial running time. This innovation provided a more robust and efficient approach to solving minimum cost network flow problems. The influence of Tardos's work extends to other researchers in the field. Andrew Goldberg, for example, developed efficient maximum flow algorithms using similar scaling techniques. Éva Tardos improved upon Tardos's algorithm for minimum cost flow, further reducing its running time. These researchers have acknowledged the significant impact of Tardos's work on their own research, solidifying its place as a cornerstone in the field of network optimization. Following her groundbreaking work on minimum cost flow algorithms, Éva Tardos turned her attention to online algorithms and approximation algorithms for combinatorial optimization problems, particularly those related to cut problems. This area of research addresses scenarios where complete information about a problem is unavailable at the outset, necessitating algorithms that make decisions incrementally as new data arrives. This contrasts with classical optimization, where the entire problem instance is known beforehand. One significant area of her contribution lies in the realm of online standard tree problems. The standard tree problem in its classic form, seeks the minimum cost tree connecting a given set of vertices, known as terminals, within a graph. Additional vertices, called Steiner points, may be included in the tree to minimize the overall cost. The online version of this problem presents a unique challenge. Terminals arrive sequentially, and the algorithm must incorporate each new terminal into the existing Steiner tree without knowledge of future arrivals. This constraint makes it impossible to achieve optimal solutions in general, motivating the search for algorithms with provable approximation guarantees. Designing effective online algorithms for the Steiner tree problem demands careful consideration of how to balance the cost of connecting new terminals with the potential for future arrivals to alter the optimal tree structure. An naive approach of simply connecting each new terminal to the closest vertex in the existing tree can lead to poor performance, as it may create long, circuitous paths that could have been avoided with foresight. Tardos, along with collaborators, developed innovative online algorithms that achieve competitive ratios, guaranteeing that the cost of the online solution is within a bounded factor of the optimal offline solution, even in the worst-case arrival sequence. Consider, for example, a simple online Steiner tree algorithm where, upon arrival of a new terminal, the algorithm connects it to the existing Steiner tree via the shortest path. While seemingly straightforward, analyzing the competitive ratio of this algorithm requires sophisticated techniques to account for the potentially adversarial order of terminal arrivals. Tardos's work provided a framework for analyzing such algorithms and developing improved strategies that minimize the impact of unfavorable arrival sequences. Her approach often involved techniques such as primal dual methods, which leverage the relationship between a linear programming relaxation of the problem and its dual. By constructing feasible solutions to both the primal and dual problems in tandem, one can obtain bounds in the optimality gap and design approximation algorithms with provable guarantees. Randomized rounding, another key technique, involves solving a linear programming relaxation and then randomly rounding the fractional solution to obtain an integral solution. This approach allows one to exploit the power of linear programming while still obtaining a feasible solution to the original combinatorial problem. Beyond Steiner trees, Tardos made significant contributions to approximation algorithms for multi-cut and sparsest cut problems. The multi-cut problem involves finding a minimum cost set of edges that, when removed, disconnect a given set of sourcing pairs in a graph. The sparsest cut problem seeks to find a cut in a graph that minimizes the ratio of the number of edges crossing the cut to the product of the sizes of the two resulting vertex sets. Both of these problems have wide-ranging applications in network partitioning, clustering, and other areas. For instance, in network partitioning, the multi-cut problem can be used to divide a network into smaller subnetworks while minimizing the number of connections between them. This can be useful in designing communication networks, distributing data across multiple servers, or isolating faulty components in a system. The sparsest cut problem, on the other hand, can be used to identify bottlenecks in a network or to cluster data points based on their connectivity. Approximation algorithms for multi-cut and sparsest cut problems are particularly important because these problems are known to be NP-hard, implying that finding optimal solutions is computationally intractable for large problem instances. Tardos, in collaboration with others, designed approximation algorithms that achieve polylogarithmic approximation ratios for these problems. These algorithms guarantee that the cost of the approximate solution is within a polylogarithmic factor of the optimal solution. This represents a significant achievement as it provides a practical way to obtain near-optimal solutions for these important problems, even when optimal solutions are beyond reach. The significance of these approximation ratios lies in the context of NP-hardness. Since finding optimal solutions is believed to be impossible in polynomial time, approximation algorithms provide a valuable alternative. An approximation ratio of, say, logarithmic n, where n is the number of vertices in the graph, indicates that the algorithm's performance degrades gracefully as the problem size increases. This is in contrast to algorithms that may provide better solutions in some cases but have no provable guarantees on their worst-case performance. Her work in this area built upon earlier research in linear programming relaxations and randomized rounding techniques. Researchers such as Leighton and Rao had previously used linear programming to obtain approximation algorithms for the sparsest cut problem. However, Tardos and her collaborators developed more sophisticated techniques that achieved improved approximation ratios and extended the results to a broader class of cut problems. Specifically, they leveraged semi-definite programming relaxations and more refined rounding schemes to obtain better guarantees on the quality of the approximate solutions. The influence of Tardos's work on approximation algorithms for cut problems can be seen in the subsequent research of other prominent researchers. For example, Sanjeev Arora and Satish Rao built upon her techniques to develop improved approximation algorithms for related problems in graph partitioning and clustering. These researchers have explicitly cited Tardos's work as a key inspiration for their own research, highlighting its lasting impact on the field. Furthermore, her work has influenced the design of practical algorithms used in various applications, including data mining, image segmentation, and social network analysis. The theoretical underpinnings provided by her research have enabled the development of more efficient and reliable algorithms for these real-world problems. Semi-definite programming relaxations, coupled with refined rounding schemes, proved instrumental in securing enhanced guarantees concerning the approximate solutions to a broader class of cut problems. Subsequent research by prominent figures illustrates the influence of Tardos's work on approximation algorithms for cut problems. Sanjeev Arora and Satish Rao, for example, expanded upon her techniques to formulate improved approximation algorithms applicable to related problems in graph partitioning and clustering. These researchers explicitly acknowledged Tardos's work as a central inspiration for their own investigations, underscoring its sustained impact within the field. Her contributions have further informed the design of practical algorithms employed across various applications, encompassing data mining, image segmentation, and social network analysis. The theoretical foundations established through her research have promoted the creation of more effective and dependable algorithms tailored for these real-world challenges. Beyond the realm of cut problems and approximation algorithms, Tardos made substantial contributions to algorithmic game theory and mechanism design, particularly concerning network congestion games, selfish routing, and the quantification of efficiency loss due to selfish behavior. known as the price of anarchy. These areas investigate how strategic interactions among multiple agents impact the overall performance of a system, with a focus on designing mechanisms that can align individual incentives with system-wide goals. Network congestion games model situations where multiple players share a common resource, such as a network, and each player's cost depends on the level of congestion on the resources they use. Imagine drivers choosing routes in a city. Each driver aims to minimize their travel time, but the time spent on a particular road increases as more drivers use it. Analyzing equilibria in these games, where each player chooses a strategy that minimizes their cost given the strategies of others, presents significant challenges. These challenges stem from the complex interdependencies among players' decisions and the potential for multiple, possibly inefficient, equilibria. Tardos' work provided crucial insights into the structure of these equilibria and their impact on overall system performance. A central theme in Tardos' work on network congestion games is the quantification of the price of anarchy. This metric measures the ratio between the worst-case social cost in any Nash equilibrium and the optimal social cost achievable by a central planner. Essentially, it captures the loss of efficiency resulting from decentralized, selfish decision-making. Tardos, along with collaborators like Kim Rufforden, established fundamental bounds of the price of anarchy in various network routing models. For instance, they showed that in network congestion games with linear cost functions, where the cost on each resource increases linearly with the amount of traffic, the price of anarchy is at most 4/3. This result, published in the Asterisk Journal of the ACM Asterisk, provides a concrete upper bound on the inefficiency caused by selfish routing in a relatively simple, yet widely applicable, model. The proof involved a clever combination of techniques from convex optimization and game theory, demonstrating a deep understanding of the underlying mathematical structures. This bound of 4/3 has become a benchmark in the field, serving as a point of comparison for more complex models and algorithms. Tardos and Rufforden further extended these results to more general classes of cost functions. They investigated the price of anarchy in games with polynomial cost functions, demonstrating that the price of anarchy increases with the degree of the polynomial. These findings, published in Asterisk Mathematics of Operations Research Asterisk, offer insights into how the complexity of the cost functions affects the efficiency of equilibria. The analysis required sophisticated mathematical tools and a careful consideration of the trade-offs between individual costs and social welfare. The significance of these bounds lies in their ability to provide guarantees on the performance of real-world systems, even when individual agents act selfishly. For example, these results can be used to assess the impact of selfish routing on traffic congestion in transportation networks or to evaluate the efficiency of resource allocation in communication networks. By understanding the price of anarchy, system designers can make informed decisions about infrastructure, investments, and traffic management strategies. Beyond bounding the price of anarchy, Tardos also explored mechanisms for mitigating its effects. She investigated the design of incentive schemes that can encourage cooperation and improve efficiency in networked systems. This work draws upon the principles of mechanism design, a field that seeks to create rules of the game that align individual incentives with desired social outcomes. One approach she explored involves the use of tolls or taxes to discourage the use of congested resources. By charging users for the negative externalities they impose on others, it is possible to internalize the social cost of congestion and incentivize more efficient routing decisions. Tardos, in collaboration with Éva Tardos, developed algorithms for computing optimal tolls in network congestion games, demonstrating that carefully chosen tolls can significantly reduce the price of anarchy. Their work, appearing in Asterisk Games and Economic Behavior Asterisk, provides a practical framework for implementing tolling schemes in real-world transportation networks. Another line of research focuses on the design of truthful mechanisms, which ensure that players have an incentive to report their true costs or preferences. Truthful mechanisms are particularly important in settings where the system designer lacks complete information about the player's characteristics. Tardos and her colleagues developed truthful mechanisms for various network design problems, including the problem of allocating network bandwidth to users with different quality of service requirements. These mechanisms guarantee that the resulting allocation is both efficient and fair, even when users act strategically. Tardos' contributions to algorithmic game theory and mechanism design build upon earlier research in these fields, most notably the work of Rufforden and Nissen. Rufforden's work on the price of anarchy provided the foundational framework for quantifying the inefficiency of selfish behavior in networked systems. Nissen's contributions to mechanism design laid the groundwork for designing incentive-compatible mechanisms that can achieve desired social outcomes. Tardos extended and refined these ideas, applying them to a wide range of network optimization problems and developing new techniques for analyzing and mitigating the effects of selfish behavior. For example, her work on bounding the price of anarchy in network congestion games with linear cost functions directly builds upon Rufforden's earlier results on the price of anarchy in simpler routing models. Similarly, her work on truthful mechanisms for network design problems draws upon Nissen's framework for designing truthful auctions and allocation mechanisms. The influence of Tardos' work on algorithmic game theory and mechanism design can be seen in the subsequent research of many other researchers in the field. Her results on the price of anarchy have been widely cited and extended to more complex models of network congestion. Her algorithms for computing optimal tolls have been implemented in real-world transportation networks. Her truthful mechanisms have been used to design efficient and fair resource allocation systems in various applications. Specifically, her work directly influenced the research of Noam Nissen, who applied similar techniques to the design of online advertising auctions. Building on Tardos' framework for truthful mechanism design, Nissen developed novel auction mechanisms that incentivize advertisers to bid truthfully for online ad slots, leading to more efficient allocation of advertising resources. This demonstrates the tangible impact of Tardos' work on real-world applications of algorithmic game theory. In summary, Éva Tardos' contributions to algorithmic game theory and mechanism design are substantial and far-reaching. Her work on network congestion games, selfish routing, and the price of anarchy has provided crucial insights into the behavior of networked systems and the design of mechanisms that can improve their efficiency. Her research has had a significant impact on both the theoretical foundations of these fields and their practical applications in areas such as transportation, communication networks, and online commerce. Éva Tardos' intellectual trajectory reveals a remarkable capacity to synthesize disparate mathematical and computational concepts into elegant and practical solutions. Her foundational work in combinatorial optimization, particularly her contributions to network flow theory, established a bedrock upon which subsequent generations of researchers have built. The efficient scaling algorithms she devised for minimum cost flow problems, for instance, transcended mere theoretical exercises. They provided the computational muscle necessary to tackle real-world logistical challenges. These algorithms, by cleverly exploiting problem structure, enabled the optimization of resource allocation in complex networks, a capability with profound implications for supply chain management and transportation planning. The design of efficient algorithms constitutes a recurring motif throughout Tardos' career. She consistently sought algorithms that are provably correct and computationally tractable, even for problems of considerable size and complexity. This commitment to efficiency extends beyond worst-case analysis to encompass average case behavior and practical performance. Her approximation algorithms for NP-hard problems, such as those arising in scheduling and facility location, exemplify this philosophy. These algorithms, while not guaranteeing optimal solutions, provide near-optimal solutions in polynomial time, a crucial compromise in situations where exact solutions are computationally infeasible. The impact of this approach is felt across diverse domains, from airline scheduling to telecommunications network design. Networked systems form another central thread uniting Tardos' diverse research contributions. She recognized early on that many real-world systems, from the internet to social networks to economic markets, can be modeled as networks and interacting agents. This perspective led her to investigate the behavior of these systems from an algorithmic and game-theoretic viewpoint. Her work on selfish routing, for example, eliminated the potential for inefficiency in networks where agents act independently to minimize their own costs. She quantified this inefficiency through the concept of the price of anarchy, which measures the ratio between the worst-case Nash equilibrium and the optimal social welfare. This framework provides a powerful tool for analyzing the impact of decentralized decision-making on network performance and for designing mechanisms that can mitigate the negative effects of selfishness. Tardos' influence on the field of theoretical computer science extends far beyond her specific technical contributions. She has fostered a vibrant research community through her mentorship of numerous students and postdocs, many of whom have gone on to become leading researchers in their own right. Her commitment to collaboration and her ability to inspire others have created a legacy of innovation and excellence. The impact of her work is evident in the widespread adoption of her algorithms and techniques in both academia and industry. Her research has laid the groundwork for many modern algorithms and game-theoretic approaches employed in network design and resource allocation. The novel aspects of Tardos' research often lie in her ability to identify and exploit the underlying mathematical structure of seemingly intractable problems. She possesses a remarkable talent for formulating problems in a way that makes them amenable to algorithmic solution. Her work on online algorithms, for example, demonstrates this ability. She developed algorithms that can make decisions in real time with limited information about the future, a crucial capability in dynamic environments such as online auctions and resource allocation systems. These algorithms provide provable performance guarantees, even in the face of uncertainty, a testament to her deep understanding of the interplay between computation and information. The modern relevance of Tardos' work is undeniable. As our world becomes increasingly interconnected and data-driven, the need for efficient algorithms and robust network designs grows ever more pressing. Her contributions to combinatorial optimization, network flows, approximation algorithms, and algorithmic game theory provide the foundational tools needed to address these challenges. Her work has had a tangible impact on areas such as transportation, communication networks, and online commerce. For instance, her algorithms are used to optimize the flow of traffic in transportation networks, to allocate bandwidth in communication networks, and to design efficient advertising auctions. Her insights into network congestion gains continue to resonate in the design of modern transportation systems, informing strategies for managing traffic flow and incentivizing commuters to adopt more efficient routes. Similarly, her work on selfish routing provides a framework for understanding and mitigating congestion in communication networks, ensuring reliable delivery of data across the internet. The mechanisms she developed for truthful mechanism design directly influenced the research of Nissen, whose work on online advertising auctions showcases the practical impact of her theoretical contributions. Nissen's novel auction mechanisms, built upon Tardos' framework, incentivize advertisers to bid truthfully for online ad slots, fostering a more efficient allocation of advertising resources. Reflecting on her career trajectory, one cannot overlook her significant contributions to the field as a woman in computer science. In a field often characterized by gender imbalance, she has served as a role model and an inspiration for aspiring female computer scientists. Her success demonstrates that with talent, hard work, and determination, women can achieve excellence in even the most challenging fields. Her presence has helped to create a more inclusive and diverse research community, benefiting the field as a whole. Éva Tardos' work is a testament to the power of theoretical computer science to address real-world problems. Her contributions have not only advanced the state of the art in algorithm design and network analysis, but have also provided practical tools for improving the efficiency and performance of networked systems. Her legacy as a researcher, mentor, and leader will continue to inspire generations of computer scientists to come. She exemplifies the ideal of a scholar who combines intellectual rigor with a deep commitment to solving impactful problems, leaving an indelible mark on the field and on the world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.